we are getting to the end of the first semester of classical mechanics, but there's so many Lagrangian problems that you could do that I can't stop. So I'm going to do a few more. I'll do a semester review, and I'll post that too. But I gotta do a few more. I can't stop. Can't stop. Okay. So here's the problem. I have right here a stick, and that stick's going to rotate with some angular velocity omega, and there's a bead that can slide along that. And so what's the motion of that bead as the stick rotates up? And there's a lot of variations of this problem that I want to do, but let's just see how far we get. Okay. So with Lagrangian, we know we need to write the Lagrangian, but we need to first pick the generalized coordinate. Okay. And yes, it moves in 2 dimensions, but there's only one generalized coordinate, right? I could say this whole thing is described by the value s, the length up the stick it is. The angle is set. That's a set angle. It's moving on its own. I can't control that, so I don't need to make that as a variable. Now I need to write the kinetic energy. So of course we write the kinetic energy as 1/2 m x dot squared plus y dot squared. I know that, right? I know the kinetic energy in Cartesian coordinates, so I always want to write that down. Now what I want to do is to write my generalized coordinate in terms of my Cartesian coordinates. So if that's my position s along the stick, and this is the angle omega t, right, saying it starts right down here, omega t is the angle, then I can just treat omega t as the angle theta. So I get x is s cosine omega t, y is s sine omega t. Now I can take the derivatives and square them and plug them into the kinetic energy term. So let's take the derivatives. X dot is going to be equal to the derivative of s dot. And again, if you haven't been following along, this is part of a playlist, and the whole playlist is down below. And we write time derivatives as the dot notation. So a dot means the first derivative with respect to time. A second dot means the second derivative with respect to time. Okay. So I have a product here, so I'm going to take the derivative of s dot times cosine omega t. Now I've taken the derivative of this times that. So the derivative of cosine is negative sine. So I get negative s. I'm going to have to take the derivative of the inside. I'm going to put it right here, omega sine omega t. Right? So take the derivative of the first, s dot, times this, plus the derivative of this times that, but I have to take the derivative of the inside too. Okay. Now we can do y dot. Y dot is s dot sine omega t plus s omega cosine omega t. That's a parenthesis. Now I need to square both terms and add them together, and maybe you see what's going to happen, but I'm going to do it the long way because I care. I care about you. So x dot squared is going to be s dot squared cosine squared omega t plus s squared omega squared sine squared omega t minus 2s s dot omega cosine omega t, leave that parentheses off, sine omega t because it's not going to matter. And then I'm going to write y dot squared is equal to s dot squared sine squared omega t plus s squared omega squared cosine squared omega t plus 2s s dot omega cosine omega t sine omega t. So now when I add those two things together, I have a plus and a minus 2 thing there. They cancel. Also, x dot squared plus y dot squared, if I take these two terms and add them together, then I get s dot squared factors out, and I get cosine squared plus sine squared, which is 1. So this is going to be equal to s dot squared. And then these two terms, same thing happens, sine squared, cosine squared, factor out the s squared, omega squared. And that's it. So now I can write my kinetic energy term as 1/2 m s dot squared plus s squared omega squared. Now my potential energy is pretty easy. It's just mgy and that's going to be mgs sine omega t. So let's put it all together and write our Lagrangian. Delete this stuff so we can have as much room as we want. And more. All the room. L, t minus u, so it's going to be 1/2 m s dot squared plus s squared omega squared minus the potential minus mgs sine omega t. Delete that. Okay. Now, the Euler-Lagrange equation says that S dot has to agree with the following. The partial of L with respect to S is the time derivative of the partial of L with respect to S dot. That's the Euler-Lagrange equation. That's the key. L equals t minus u, and that equation are the key. Well, let's just do it. The partial of L with respect to S is going to be equal to, well, I'm looking for the s's, right? So here's an s. So I get the derivative of s squared, but there's a 1/2 m. So I get m s omega squared. And then over here I have an s, and it's just a partial, so it's good, that just goes away. mg sine omega t. Okay, now let's take the partial of L with respect to S dot. Well, there's only one S dot term, it's right there. So that's pretty easy. This is just going to be ms dot. And then if I take the time derivative of that, the mass doesn't change with time. So I just get the derivative of S dot with respect to time, so I get a double dot. Now that has to be equal to that. So now I'm done. ms double dot ms omega squared minus mg sine omega t. The masses cancel. S double dot s omega squared minus mg sine omega t. Okay, I mean, just a little quick check, right? I started with an angle of 0. And what if omega is 0, right? So I have a flat board and it's not moving up. Well, then the acceleration in the s direction would be 0. S double dot should be 0. So if omega is 0, that's 0. Sine of 0 is 0, so I get 0. Now, if you wanted to start it at some angle at time t equals 0, you can see that this term would not be 0. There'd be some constant in there, and it'd be the acceleration of a block sliding down a plane. Which is what you would expect. So I'm okay with this. I think this is okay. Now, how do we model this? And not just model it, we're going to make a 3D model. Of course, I'm going to use WebVPython. Of course, I'm going to use the Euler, it's Euler method of numerical calculation. So break this into small time steps. Delta t is 0.01 seconds. I can calculate s double dot. I'm not going to write that out. And then use that to update s dot. And then use that to update s. And then update time. And then do it all over again. Okay. Now, in order to make a visual representation of this, I'm going to have my stick, I'm going to have my mass, but I'm going to need to convert back. I'm going to need to convert back to Cartesian coordinates because WebVPython uses Cartesian coordinates. Okay. Let's do it. I'm going to need some values too, and we can pick our values. So switching to the computer. I am going to give you the code. You don't have to worry about that. I'm going to use the same values I used. I did this before. I'm not going to make a graph. I'm just going to make an animation. So I need g is 9.8. I've already assumed that g is a downward vector, right? So I don't put negative g. I don't really need the mass, 0.1, but I put it in there anyway. R is the length of the stick. It's a 1 meter stick. Let's start with S is equal to 0.5, so it's halfway up the stick. Omega equals, I'm going to pick 3 radians per second, completely choiced. I do need to start with the value of s dot. S dot is equal to 0. Let's pick that. Now I want to draw my stuff. So I am going to need my x and y coordinates. So let's just say my initial x value is s and my initial y value is 0. It's going to be like that. So I'm going to draw the stick. Let's just make the stick. The stick, it's a cylinder. The position, it's going to be based at the origin. So the cylinder object, it has two main properties. The position is the location of one end of the stick, and then axis is a vector from the beginning, that point, to the other end. So this is going to be vector 0, 0, 0. Now, I'm just going to start off with the axis at 0 in the x direction, right? I don't have to make an equation for that. I will do that later. Axis is vector r 0, 0. And then let's give it, no, I'm not going to give it a color. Did I give it anything else over here? I just want to see what I did. Oh, radius. I do need the radius. I went with radius is r over 100. Just an FYI, if you leave the radius off, it says, okay, I'm going to do it 1. And then so I'd have a 1 meter thick stick. That's probably not what you want. Right here, you'll see that it doesn't really fit in my thing very well, and that's just because I have it zoomed in really a lot, and also because it centers things on the origin. So if you move this over here, it'd look a little bit better, but I don't really care. I don't want to waste all my time on that. Okay, let's just animate the motion of the stick, and then we'll add the bead. Okay, just for completeness. So over here, I need a time. T is 0. dt is 0.01, and let's just run it for a second. While t is less than 1, rate 100 says don't do more than 100 calculations per second, so that's real time. Now I'm going to actually just move the stick, so I'm going to change the axis value. Stick.axis, and there's more than one way to do this, but I'm going to do it this way, is equal to the vector r times cosine omega times t, r times sine omega times t, and then 0. Because that's how it's going to change in the x and y value, which is very true for my bead too, but my bead's not going to be at the position r. Now I'm going to update time. T equals t plus dt. If you leave that off, it's just embarrassing. And I've done it so many times. There you go. Now it looks a little weird just because it zooms out a little bit, but that's fine. Now let's make our bead. It's a sphere. Its position, I already have x and y. So its position is going to be vector x, y, 0. Its radius is, let's say, I think I said r over 50. What did I do before? R over 30. I did r over 30. You just want to make it look big. And I'm going to make it yellow. Color equals color dot yellow. Spell it right. And then I'm going to make it leave a trail. Make trail equals true. That's that. Okay. So now I can just animate the motion of that by calculating s double dot and then using that. So let's go up here, calculate s double dot. S d dot, that's what I use for double dot. Now I'm going to look at my board over here. I have s times omega squared minus g times sine omega times t. Right. Now I can update s dot. S dot is s dot plus s double dot times dt, and then update s. S equals s plus s dot times dt. Now I can recalculate x and y. So let's do that. X equals s times cosine omega times t. Y equals s times sine omega times t. And I can move my thing. So bead.pos, scroll up a little bit, is equal to vector x, y, 0. So, it's a little bit different. Instead of like moving the bead, updating the position of the bead, I just calculate the position and I move it each individual spot. So it's not, the numerical calculation is in s double dot, but I'm just moving it. And then my stick gets moved already, so I think we should be done. I didn't even save it. Okay, so now we notice a couple things. Number one, notice it looks cool. Number two, it went past the pivot point, right? And I don't actually want it to go past the pivot point. So let's see, how did I do that before? I said, what did I do? Okay, this is it. So if S is less than 0, right? Then if the S value is less than or equal to 0, then I want it to just stop. I don't want it to keep updating. So just stick down there. And if it's at S equals 0, it won't move anyway. So down here, let's say if S is greater than 0, then I'll update S dot and S double dot and S double dot and S. Else, I'm going to just say S equals 0. Let's see if that works. Yep, it stopped. So it kept moving, but the bead stopped. Let's just try with a lower angular velocity. Yep. And that's what I want. I want it to be real, right? I want it to be realistic. Now we need to go to the other end. What if it gets to the other end of the stick? So let's just put this angular velocity at something like 5 and see what happens. So it doesn't know that there is or is not an end to the stick. It doesn't know. It's just a dumb computer. I'm sorry, computers, don't get mad. It's just a computer. So what I want to do is to say, okay, if the bead is past the end of the stick, then I'm just going to let it do projectile motion. And that would be like flinging the thing off. Okay, let's see if we can do that. Okay, so what I'm going to do is on my bead, I'm going to add a new property. I'm going to say on equals true. So this is if it's on the stick. And if it's not on the stick, then it'll be projectile motion. So up here, the first thing I want to do is to say, is it on the stick? So if bead.on, right? That's either true or false. It's a Boolean variable. So if it's on, then do all this stuff. So I'm going to highlight all this stuff right here and tab and indent that. So that's if it's on the stick. So I need to go up here and say, well, how do I know if it's on or off? Let's say end is vector r times cosine omega times t, r times sine omega times t, 0. So that's the end of the stick. And then I can just say if mag, not s. No, let's just say s. If s is greater than mag of end, right? Because the end moves. Or I could just say if s is greater than r. That was dumb. If s is greater than r, it's off the stick. And then I'm going to say bead.on equals false. So it's not on anymore. Okay, so then it wouldn't do all this stuff. And then down here, oh, actually, you know what? It could come back. No, I think it'd be okay. So now down here, that's if the bead is on. If the bead is off, I'm going to say else, and I want to calculate the velocity of the ball, and then just update the ball's velocity with gravity. But what is the velocity of the ball when it leaves? What is the velocity of the ball? That one's not so easy. Well, if we go back up to our board, I think we have an idea, right? Because I calculated s dot. And I know x dot and y dot. I erased it. Let's put x dot and y dot back on the board, because that x dot, y dot are the Cartesian velocities, and we want those in terms of s dot and omega. So switching back up to the board for a second. Okay, I erased a lot of the important stuff, but I think I can do it. So I had x is s cosine omega t, y is s sine omega t. So x dot is going to be s dot cosine omega t minus s omega sine omega t. Y dot is s dot sine omega t plus s omega cosine omega t. So the velocity is x dot x hat plus y dot y hat plus 0 z hat. So I can calculate that and then use that in the next step. Okay, so that's what I'm going to use. Going back over here. So let's just calculate that every single time up here. I need to calculate that up here every single time. I technically need to do it ahead too, but let's just say ball dot v equals vector. Actually, I'm going to write this as two parts. Let's say x dot is equal to s dot times, why did I just forget? Cosine omega t minus s times omega times sine omega t. And then, oh, almost made an error there. You should have caught me. Y dot is equal to s dot times sine omega times t plus s times omega times cosine omega times t. And then I can write my velocity as the vector x dot, y dot, 0. So I'm going to continually calculate that ball's velocity. And then once it leaves up here, I'm going to just update the velocity of the ball. Ball dot v equals ball dot v plus vector 0, negative g 0. I need that as a vector times dt. Right? That's how much the velocity is going to change during that time interval. Now I can update the ball's position. Ball dot pos equals ball dot pos plus ball dot v times dt. And then I still update time and I move the stick. I think that will work. Let's just try it out. Let's save it. I haven't saved in a long time. That's just a bad idea. Okay. Run it. Something happened. Can't find, oh, ball. It's a bead. It's not a ball. Bead, bead, ball, bead. It was a dumb mistake, but that's okay. Dumb mistakes are fine. It's not catching dumb, or not fixing them. Oh, there's another one. It's the bad thing. Okay, let's see. I might have missed another ball, but nice. Okay, I like it. I like it a lot. Now, I'm going to give you some homework, because when I say homework, I mean problems that I want to do, but I don't want to do them right now, so I'm giving you homework. So let's go to the board, and I have two excellent homework problems for you. So the homework problem number 1 is, suppose that I have a different problem. It's very similar, but now I start right here at theta, and it moves down like this with an omega. And it's a block. It's a block that can slide with friction. So the question is, would this lose contact? I mean, you can imagine if this starts up high enough and the angular velocity is fast enough, this would just goop and it would just leave it, right? But the same thing true is it's also sliding down. So I don't know, it's a fun situation. Okay, the number 2 one is this. It's like a catapult. So here it starts right here and it has an angular acceleration alpha. Same problem. And then you could, I wonder if it would ever just leave, if it would leave. I was really thinking about this as a bead sliding off the end. But then here, this angle is 1/2 alpha t squared, right? This one's actually not too hard to do to code if you just don't worry about the contact force. Remember, up here, if you want to find the contact force, then I need to have 2 variables. I would need to have this as r and theta as a variable. And then I could use the following. The partial of L with respect to, well, I could still call that S. S plus lambda partial of F with respect to S equals the time derivative of the partial of L with respect to S dot. And then I'd have another one for theta. The partial of L with respect to theta plus lambda partial of F with respect to theta equals d dt partial of L with respect to theta dot. And then F is a function of S and theta equals a constant. You can use that. And then lambda partial of L with respect to S is your constraint force. And you'd want to say, when does that go to 0? I think they're good questions. Maybe they'll be on the test. I don't know. But don't forget, playlist down below, code down below. I'm going to do a couple more Lagrangian problems, probably. The end.